Good morning. Good morning. Today is 7/2, Snakes in the Plain, day 3. It should be a short one here, and then following this one, I believe we're going to have formative posted for you to complete and turn in, hopefully by the end. Well, it should be by the end of the day, because between this and that shouldn't take you over, should still take you less than an hour. So yesterday, what we did was we took, oh crumb, do this one again. I had one, I forgot to put my picture in there, but that's okay. What we had to reorient our function so that we could integrate in a different direction. And the reason for that, this is a prime example of it, because as I'm coming through, if I was integrating vertically, or when I say vertically, I'm saying with respect to the x-axis, my heights here, okay, my heights would be with respect to the x-axis, where I'm taking big height minus little height. But notice my bottom function changes right over here, and then how do I find the height? Because that's the same function. And it's kind of, I got to find both conic sections, because this is basically a sideways parabola, and I have a positive half and a negative half, which means I need to break that into two independent functions. So then I got two different bottom, and it's just bottom line, it's more difficult than it is it's easier if we just reorient our function and we go sideways. And a big kicker for that would be, see how your function is defined for you. It's x in terms of y. And so basically what we're going to do is we are going to lay our rectangles horizontal again, so that we have the same height. We're using the same functions all the time to find this height. And it's always going to be right curve minus left curve, or right curve minus left curve. So as I'm going here, this particular problem is way easier to integrate with respect to y than it is x. Because if it is with respect to x, like I said, I'm going to have to divide this, and I'm going to have to do an integral from this point to this point of that top curve minus that bottom curve. And then I'm going to have to go from this point to this point, whatever it is. And then I got to split this parabola into this curve minus that curve. And I got to find the positive and negatives of it, and it's just a little too complicated. So it's easier to say, hey, let's reorient this bugger. Come on. Reorient this bugger in terms of x. So how do I do that? Well, because my rectangles are sideways, I can kind of think of this as, here is my first height, okay? So I'm taking this one, which is going to be like an x2, y2. And then my other height is this one to find the actual height of that purple one. Now my function changed. This is like my x1, y1, because it's first. And what I do is I take the red line minus the green line to get the purple line. And that actually gives me my height. But notice my height here, my height is going to be my delta y, my change in y. That's a really small change in y for how thick that rectangle is going to be. So this rectangle orientation is really important, because if my thickness of my rectangle is with respect to the y-axis here, what's going to happen is I have to be integrating with respect to y. And if I'm integrating with respect to y, this whole bugger needs to be a function in terms of y, where I'm plugging y values in. So how do I do that? Well, I move and shake along here, and bottom line, I took this function and I solved it for x, so x is going to equal 3 minus y, and up here, this one was already solved for x. So when I'm looking here, well, first and foremost, I'm going to take my right curve, my bigger curve, which is this one, or my greater curve, which is going to be 3y minus y squared, minus this lesser curve, which is going to be my 3 minus y, dy, because that is how I'm going to get that height. That is the height times my width right there, is my width is my dy. But the next question is, what are my limits of integration? Well, my limits of integration, I need to know what is this point and what is this point. I need to know the y value of this point and this point. Well, I can see the top is pretty easy. The top is at 3, but what's the bottom at? Well, all I still do is I take my 3y minus y squared, I take that curve, I take my greater curve, and I set it equal to my lesser curve, and I say y squared, subtract that 3, I get minus 4y plus 3, and I want to find my points of intersection. Points of intersection, okay? And those are my points of intersection. Those are going to be my limits of integration. So I get a 0. It's going to factor really nice for me. Y minus 3, y minus 1. So I get y equals 3 and y equals 1. So I know this point really is something comma 3. Is it? Something comma 3? No. Come on, Kruger. It's something comma 3. See, I'm getting all backwards here because I don't like to change my x and y because it twists my mind. But that one is something over something up 1, okay? Because these, right, from here to here, those are going to be my limits of integration. These are all my delta y's for my thickness that I'm summing up. So I'm integrating from 1 to 3. And you would just skedaddle your little fingers to your calculator and you would type that in. And I think when you type it in, you're going to find out that equals 4/3. Okay? Now, that's not to say we can't do it a different way in terms of x, but it's much more complicated that way. So we want to see our setup and our answer. And a lot of these area problems like this are the ones that you would use your calculator for anyways on the AP test. And also understand, if I took this integral from 1 to 3 and I simplified and I cleaned that integrand up a little bit, it's going to be plus, come on. If I clean this up, and what are you talking about cleaning it up? Well, what I'm talking about is distributing that and seeing that as a negative and a plus and saying negative y squared plus 4y minus 3 dy. This is also going to equal 4/3. Why did I clean it up like that? Because that's a very easy function to evaluate, integrate, and evaluate. But we're just not going to do it, okay? And we're going to come to the next one here. Find the area of the shaded region bounded by. Now notice, this one we're probably going to go in terms of x2. That square root's going to come across the top there. Because it's usually, generally when they have a function, x equals a bunch of y's, and it's not y equals my function in terms of x, usually that means you want to think about dy, integrating dy. And what I'm talking about, it's saying, hey, think about laying your rectangles sideways, okay? Because it's going to be easier, okay? And if I did that sideways, well, I know I'm taking my integral of something dy, which again, remember, that means these limits on here need to be in terms of y. And when I think about what comes in here, I go right curve minus left curve is how I find the height of my rectangles, which is going to be 2 square root of y minus y dy. And now I would need these points that I have here. Well, how would I find out the points? Well, I guess I would have to find the intersection of this line and this line. And how would I do that? I would use substitution. And if I plugged my y as 1 here, that would mean x. This is going to be 2, 1, right? And bottom line, I'm going from my y's, I'm going from 0 to 1 if this is the way I'm integrating. I go 0, 1. I don't even need to do a system on, okay? And I can type that little bugger into my calculator, and when you type that in, I think you're going to find this integral equals 5/6, okay? Set up and go. Well, let's say I went the other way. What do you mean the other way? Let's say, and I'll just show you, it's a lot more work to do. So let's see what it is. Get rid of that, get rid of that, and we'll just see why we're doing what we're doing. And I won't waste too much time with that whole. But if I place my rectangles this way, notice right here, my upper curve changes. Okay? So I would have to have a split of an integral right here, wherever that point is, and I can see this and this. I lost my equals on that guy. Equal. Those two intersect right here at 1, 1. And I can see these two, which I had listed before, they intersect at 2, 1. Okay? So if I did this, I could also say, what's my integral? If I went in terms of x with these green rectangles, I could integrate from 0 to 1. And if I did that, because this one could be done either way, if I did that, I would be, well, top minus bottom. Here's my top curve. So I'm taking x minus the bottom curve. Ooh, that would mean I would have to solve this for y. That means I need to take my x equals 2 square root of y. Okay, because remember, this is going to mean it's a dx, so everything in here needs to be an x. So what I'm going to do here really quick, I hope really quick, I'm going to take this x equals 2 square root of y, and we're going to say that's x over 2 equals square root of y, so y is actually going to equal x squared over 4. Okay, so if I redefine that function like that, I could say minus x squared over 4, but that's only given me this area here. Then to that, I need to add my other integral, which is going to go from 1 to 2 to get this next section from 1 to 2 of, well, now, what's my top curve? Well, now my top curve is this constant of 1, so I have to say 1 minus my bottom curve is that one there again, which ended up being my x squared over 4 dx. And after you integrate and evaluate both of those, you're going to find out together they equal 5/6. You can type them both into your calculator and check them out, because you're going to want to be able to fluently work with that calculator. Okay? Last problem we're going to have right here. Okay? Yes, it says 1988. Calculus AB problem 5. It's an old one, but they keep recycling problems like this. And when it is on the calculator active portion, okay, like I said, what they've been seeing, or what they're looking for, is they're looking for your calculus setup. They're looking at your integral with your limits. Is your integrand set up correctly? And then what does it equal? Well, we're finding the area. So what I did is I graphed this. They wouldn't expect you to graph this by heart, that one there. They're going to say, hey, grab your calculator and graph it. So I did, and I zoomed in on my windows from -1 to 3, -1 to 1, and it's this cute little curve here. And we're finding the area bounded from 0 to the square root of 6. Now, the square root of 6, it's approximately 2.449. So that's going to be somewhere right about here. I'm going to call that my square root of 6. So they want to know, what is this area right here? Okay? And if I found that area, well, what's my integral setup? My integral setup is going to be, well, I'm looking here, my top and bottom, I'm going to be a dx here, and I'm going to integrate from 0 to the square root of 6, okay? And it's going to be top minus bottom. Well, my bottom curve is 0, so that's why it's simply just the area bounded below that. So It's x over x squared plus 2. And then that's what they would want to see, and they would want you to plug that in. And you plug that into your calculator, and you're going to find out that's the ln of 2. Okay? And at the end of this lesson, and actually maybe I'll do it here in just a second, this would be one that actually you could integrate very easily by hand, and it really isn't that tough to do. So actually I'm going to do it right now, because we know the antiderivative of this, that integrand. Well, hopefully you know the derivative of the top, derivative of the bottom is 2x, so that's sitting in the top. So this is going to end up being an ln, absolute value, x squared plus 2. And we're going to evaluate that from 0 to the square root of 6. And when I do that, that's going to give me, well, what's my top? That's the ln of 8, right? Because square root of 6, square root of 6. So that's going to give me the ln. Oh, crap, need my half there. Sorry, because I got to fix for that 2, because the derivative of this is going to give me a 2. So I had to fix my half, sorry. That's going to be 1/2. And hold on, I'm going to clean this up just a skosh. And it would be 1/2 times top minus bottom. Well, my top ends up being what? And I'm keeping that half out there, and I can do that because it's going to be in both of them. So if I put that in there, I'm going to get the ln of 8, right, minus the ln of 2, because 0 squared plus 2, I get ln of 2. Well, there's my wonderful properties of logarithms. I get 1/2 times ln, that's going to be 8 divided by 2 with your properties of logs. That's going to be a 4. Well, where the heck are they getting that ln to? Well, remember, this is really an exponent on there. So that equals the ln of really the square root of 4. And the square root of 4, that's an ln too. Okay? Takes you a little bit longer algebraically, but it's ln 2. So that's how it gets there. It's one you actually could do. This next one is a fun problem, okay? And it's calculator active, so they're not going to expect you to algebraically do any of this. But this says, find a line x equals k that divides R into 2 regions of equal area. What is the interval of k? Okay, so that is saying, take this purple area we have, okay, and we want one line. Where are we going to be to slice this area perfectly in half? So I have the same amount here as I have over here. We're going to cut it perfectly in half. Well, how do we do that? Well, we know what the area is going to equal, right? We know this area is going to, the area of the whole thing was ln 2. So half of that area is going to have to be ln divided by 2 now, isn't it? Okay, so we know the area is going to be there, but how are we going to set up something to show that? Well, it's an integral. It's a cumulator of, what's my function? My function is x over x squared plus 2, and it's going to be a dx. But where am I starting from to get all this green area? What is my integral going to be there from where to k? So what I'm going to do is I'm going to say I'm going from 0 to k. What is the x value here? What is k that is going to divide that area in half? And now from here, we can do this straight into our solver as well. So I'm going to grab my solver here, and I'm going to add a calculator page. And my calculator will solve that, so we're going to say menu, we're going to say algebra, we're going to say solve, and we're going to solve, what are we solving? We are solving our menu 43, our integral from 0 to k, from 0 to k, that's where my variable is, where are you, k, tab, and then inside there we have that control divide. We're taking x over x squared plus 2 dx, and then I got to toggle over because I'm in solver. I got to get outside of my dx, and I'm going to say, when do you equal 0.5 or a half times the ln of 2, and I got to toggle over, and then I got to say, hey, the variable I'm looking for is that upper limit of k. And what is this going to equal? And it's going to equal negative square root of 2 or square root of 2. Well, when I come back here and I look, okay, or I'll come back to my my notebook, well, this has to equal the square root of 2. Negative the square root of 2 is back there. That's not where my area is. So k equals the square root of 2. They're going to be looking for that answer, and they're going to be looking for your setup, 2 points a pop. Okay? And I'm going to do this one algebraically just because it's fun in a second. And then this last one here, what is the average value of that? Well, that's the average height, remember. That is just taking my 1 over b minus a times the integral from a to b of my f of x dx. Well, that's going to give me 1 over the square root of 6 minus 0 times the integral from 0 to the square root of 6 of x over x squared plus 2 dx. Okay, that's what it is. And what does that equal? Well, on the top, really, we already found out this was ln2 because we're using part A to get this. And we're just taking this times 1 over the square root of 6. So it equals ln2 divided by the square root of 6 would be my exact value. And I really wouldn't have to even touch my calculator for that. Okay? So what I'm going to do here now is I'm going to take that previous problem there when we're taking our integral from 0 to k of x over x squared plus 2, x squared plus 2 dx, and we want to solve this for the ln2 over 2. We want to find that value of k algebraically. So what I'm going to do is I'm going to hit pause. I'm going to reveal my answer because I know there's some algebra nuts out there that really can appreciate watching this happen. All right, saddle up. Here comes the fun. So I forgot I have my squared on that before, so I added my squared after I hit pause. But what we're going to do is we're going to integrate the left side. Well, we know the antiderivative of that left side is going to be 1/2 ln x squared plus 2, and we're going to evaluate that from 0 to 2, or 0 to k. And remember, it's 1/2 times that. And all I did is, I'm like, well, I like to separate that half out when I evaluate it, and that's going to equal my 1/2 ln2. Well, when I evaluate the left side, what I do get is I get 1/2 times my upper limit, which is going to be the ln of k squared plus 2 minus the ln of 2 equals the ln2 over 2. And what I do is I multiply both sides by 2 to kill my fraction. Then I'm cruising along, and then I turned into that, and then I'm going to add an ln2 to the other side, so then I get ln of k squared plus 2 equals 2 ln2. Oh, wait a minute, don't forget, and if you forget this, that's okay, but I can take that, that's really a power up there. That's really the ln of 4 on the right-hand side with your algebra cruising along. So now I get to the ln of k squared plus 2 equals the ln of 4. Well, how do I get inside of a log? Well, I'm going to base E it, and I'm going to rewrite it, and that's what it's going to turn into. And if I base E both sides, well, those gobble each other up right there, and I get a k squared plus 2 equals 4. Well, I'm going to subtract 2, k squared equals 2, then I'm going to square root k is the square root of 2. Well, Mr. Kruger, I was back here, and I was really good up to this point, and then when you eat it, I fell apart. Well, if you forgot this came up, it doesn't matter, because you could come across and you could rewrite it here, or you could base E both sides here, and then you're going to get k squared plus 2 equals E to the 2 ln equals 2, come on, 2 ln2, okay? And then when we subtract 2, so k squared actually equals E to the 2 ln2 minus 2. And then I got to square root that. And when I square root that, well, I get k actually equals plus or minus the square root of E to the 2 ln2 minus 2. Well, remember, we're on the positive side, so we wouldn't have a plus or minus. We only want the positive one. And sooner or later, if you want the exact value, sooner or later you're going to have to see that comes up here. Well, then that's going to equal E to the ln4 minus 2, and the E gobbles up the ln, so that's the square root of 4 minus 2, which is the square root of 2, is what k is. All right. Now, they're not going to make you algebraically show that, but I just thought it would be kind of a fun fact. We're going to cruise it and bruise it right through with your solver, hopefully, because they're just looking for your setup, and then you type that bad boy in the solver. There's my value of K. So that rounds us out. Don't forget to do your formative today and send me a PDF of it. It's a lot of 7.1 going on. So hey, you have a great rest of your day. Good night.